Okay, we're going to be doing sketches, and for the next part of sketches, I was just saying to you guys, it's not going to be about actually being able to sketch them using a pencil and piece of paper. It's going to be, exercise 5B is going to be about trying to develop your understanding of where these graphs actually come from. So if we just concentrate looking at this GIF that we've got on the left-hand side here, this one has a polar equation of sine 6 theta plus 2. R equals sine 6 theta plus 2. So to begin with, that was it in its Cartesian equation. It flipped around and then kind of stretches in this sort of way. Now, I wouldn't expect you to be able to do this in your head. But what if you think about that's happening here is we're saying that these are essentially the R values, because we're saying that's what Y equals, that particular graph. We're saying that that's what R is going to be equal to. So we flip it on its side. So that's saying what the distance is from the initial pole. And then we stretch it and wrap it around the pole because we're saying that it depends on the value of theta rather than the value of x. So just think about what's happening. This was the value of y is how far away it is from here. X was how far away it was from the central point, and it's wrapping it around the whole sort of shape that we've got there. Really, it's just going to be quite good to kind of look at that and think about that and try and think what's happening, because it's just a visual tool to try and help you map from one of them to the other. But generally, it is the fact, because we have y equals, I can't remember what the graph was, I think it was sine 6x plus 2. If we have r equals sine 6 theta plus 2, the y has become the length and the x has become the angle that it has. So that's why when we put it on its side like this point doesn't move at all, because we're just saying it's the length when the angle is 0. And all of the other parts of that curve are moving from their x coordinate, wrapping around to their theta coordinate instead. Now, you're not expected to be able to kind of create these things in your head, but what we are going to be expected to try and do is think why these graphs look the way they look, okay? So this second one that I've got here, it's really difficult to see it on the board, but you should see this kind of like green sort of spirograph, like rose or flower kind of pattern that you've got in the middle. And you can see, unfortunately it goes quite fast, that this dot is representing the Cartesian coordinates. So the x is the angle and the y is the length, and how that creates this kind of spiraling pattern that we've got in the middle here. It's very, very difficult for our brains to handle going from the Cartesian to the polar, but the more that we look at sketches of them, we should be able to think about what's actually happening in them, okay? There are some other animations of these kinds of things online, so if you just search like polar coordinates in like GIFs in Google Images, you can often see some quite good animations for them, but I don't necessarily know how much they deepen the understanding. I think the next thing that we're going to do, which is actually trying to plot some points, will help us to do these, okay? So I've got 3 of them here that we're going to start thinking about what these might look like, and these are just kind of standard, very, very basic ones that we've got here. How would we sketch the following? When in all of these cases here, A is just a constant, okay? The first one is a circle, okay? So either, if I'm doing it with the axes, I would probably just have the initial line. It is just going to be a circle with radius A. Because it's just saying that it's the length of the line from the origin is A, from the pole to the point is going to be A. And that's true everywhere. I mean, that doesn't really look like a circle, but you know it's meant to be a circle, okay?
Is there any way to like recenter the arc or the origin?
Yes, there will be ways of recentering that. It's not as simple. I can't actually think of it off the top of my head. We'll see some examples where the center is not at the origin, okay? Okay, the next one is that theta is equal to alpha. Now, actually, you do technically know about this. Pardon? No, it doesn't say that r is equal to theta. It says that the angle is equal to alpha, and alpha is also going to be a constant here. It's going to be a straight line. So you need to think of all of the points. Let's pretend that alpha was pi over 4, okay? It would be a point here, here. All of these points would have, in polar coordinates, they would all have an angle of alpha. So it would end up being this line. It would not go on to the other side, because only at this point here, this angle is alpha, okay? Down here, it wouldn't have an angle of alpha. It would have a different angle. And if it was down here, and it had an angle of alpha, we would have said that r was negative, which technically you can have with polar coordinates, but I'm going to say this a few times during this unit. In edXL, we do not let r be negative. We only make r be positive. We never look at negative values of r, okay? So this one is just going to be a half line, and it's going to have an argument or an angle of alpha, and it's just coming from the pole. So that is what theta equals alpha looks like. It is just a half line. It does not go down into the other part of the graph that we've got there. It will only be a half line. And then we did actually talk about this one beforehand. This one is r equals a theta. So it's just, if it was just r equals theta, it's saying the distance from the origin is the same as the angle. So to begin with, it would be here. Then when it gets to pi over 2, it will be up here. Then it will go to pi. It's just going to be a spiral. And obviously, that's going from 0 to however many pi. Well, I can tell you how many it is. 0, pi, 2 pi, 3 pi, 4 pi. So this one is for theta between 0 and 4 pi. Obviously, if I did that all the way up to 100 pi, it's going to be a spiral that's going on for like a lot longer, okay?
You know the space between them, does it like get bigger and bigger?
Well, what is the value at this point here? What's the value of r? Pi. What's the value of r here?
Pi.
The gap between them is always going to be pi. And so this bit here, we said that was pi. Well, that's not 2 pi. That's my mistake. That's 3 pi, isn't it? That's 3 pi, that's 2 pi, and that's 4 pi. So the gap between the points where it crosses the x-axis is 2 pi, and it will be the same here. So actually, this is the kind of weird thing. As you go around, the gap is always 2 pi between the lines if you're measuring it from the pole, which is interesting. Okay, so we're just going to do this, and then we're going to stop the lesson here. So one of the ways that you can sketch these, or at least reason with them, because you're never gonna have to draw one of these by hand, but you do need to try and reason with them of what's happening, is you can sketch them using a table of values. So here I have got that r is equal to a brackets 1 plus cos theta, and I've said that technically polar angles are between minus pi and pi, but 0 to 2 pi keeps things simple. And it doesn't really matter when you're generating the values. So when you write the coordinates of polar coordinates, the theta should be between minus pi and pi. But if you're just trying to generate values by substituting in, let's just do the standard range that we deal with, which is just between 0 and 2 pi. So when I sub in 0 to this particular thing, we get 1 plus 1, so it's just 2a. When I substitute in pi over 2, this thing here becomes 0, so you just get a. When you put pi into cos, you get minus 1, so the whole thing is 0. When you put 3 pi over 2, you get that cos is equal to 0. And when you put 2 pi in, you get that cos is equal to 1, so you get 2a. So you get this pattern of being able to plot these points that you've got. So when theta is 0, r is equal to 2a. So here's the pole. So if the angle is 0, it has come 2a along in that 0 angle. When I have pi over 2 is this angle from here to here. It comes up to a. When it's at pi, the angle is, the length of the line is 0, so it goes back to the pole. When it's at 3 pi over 2, which is down here, you have a. And then when it comes back around to 2 pi, it goes to 2a over here as well. Now, what's not clear is why we have like this little bump here and this bump here. And we'll be exploring some of those things later on, okay? But this shape is called a cardioid. And you're probably thinking, well, if I didn't show you this GIF, you might have been thinking, what the hell, who cares what a cardioid is? But look how a cardioid is actually generated in real life. It's generated from 2 circles rolling around each other. And you can think of tons of areas in engineering where there's probably going to be a circle rotating around another circle. And the point that one side of a circle traces as it moves around another circle is a cardioid. So there's a lot of purpose in these things, that they do have connections to other things in life. It's not just because it's a thing that can be done. So this is what we call a cardioid. A cardioid also looks a bit like a kind of kidney shape. And yeah, it's just kind of worth thinking about how all these shapes have like inspired us to like, that they actually do come from other shapes, that a cardioid is actually to do with circles. It doesn't look like it's to do with circles, but it's these two circles rolling around each other. Yeah.
Does the red point move at all?
The red point is not moving. The red point is like consistently on that side. If you imagine it as like, I don't know, like a football and another football, if you put like a marker on one side of the football, it would be what that marker point is doing as it moves around. So it creates this cardioid shape that we've got here, okay? We're going to leave it there for today's lesson. And then in the next part, we're going to be thinking about what happens when we restrict the fact that r is not allowed to be a negative number, okay?